Hello there and welcome to this video on the foundations of linear algebra. In this first learn, we will introduce vector spaces and linear transformations, exploring their mathematical architecture and their critical role in modern technology. By the end of this module, you will be able to conceptually define vector spaces, test systems against axioms, formulate linear mappings, and understand how these abstract structures are applied in multi-dimensional computer science. And this is relatively easy if we have to speak because it bridges standard high school geometry with high dimensional computational applications. I am sure every one of you have asked the same question. Why do we learn linear algebra? And the answer is simple because it is the foundational language for modern technology, from rendering 3D graphics in real time to enabling robotic motion and powering artificial intelligence. Linear algebra provides the necessary framework for complex computations. While traditionally defined as arrows and magnitude, with magnitude and direction, modern mathematics abstracts vectors, meaning that the vectors that you have studied in high school, that you think of as a drawings, some flashes in your paper, now we don't have the same particular idea. Now it's more like general idea, which is any set of objects that support systematic scaling and addition can be treated as a vector. Okay, so covering everything from matrix systems to polynomial equations and functional curves. So a vector space is a set of objects equipped with two fundamental operations, addition and scalar multiplication. These operations must preserve membership within the set, ensuring that the structure remains closed and consistent. Now moving on to the axioms of a vector spaces, or what a vector space is defined by. So for a space to be a valid vector space, a system must satisfy specific axioms, including closure under operations, associativity, commutativity, the presence of a zero identity, the existence of an additive, inverse, and compatibility with scalar scaling. And here we present common examples of vector spaces, which include Euclidean spaces used in geometry, matrix spaces that handle component additions, and polynomial spaces where equations are structured for linear operations. And we are going to see it or to explain it clearly during our classes, presential classes. Actually, not every system is a vector space. For example, we have the set of strictly positive real numbers. It fails to be a vector space because it does not include a zero identity, which is a required component for vector addition, and it is a vital condition for this property. Now you see that vector spaces have vast applications. In engineering, they model structural loads and circuit currents. In, for example, optimization, they define boundaries for algorithms. And in signal processing, they help compress data and filter frequency grids. In the second part of this video, we move to linear transformations. This involves mapping, rotating, projecting, and altering coordinates while keeping the underlying structure of the vector space intact. Linear transformations are maps that keep grid lines straight and parallel. We are going to see this later on. So, common transformations include rotation, scaling, reflection, and projection, each providing a way to manipulate data without warping the core structure of the space. So now we define briefly the notion of linear transformation. A transformation is considered linear if it preserves the structure of the vector space. This requires strict adherence to the rules of additivity, where the transformation of a sum equals the sum of the transformations, and homogeneity, which deals with scaling continuity. So, for example, if we have a mapping T from two vector spaces V and W, so this T is linear only if and only if we have the additivity property and the homogeneity property, as you clearly see. So here we present some examples of transformations. We have, for example, rotation, which rotates elements by fixed angles, keeping coordinate length conserved while shifting positions smoothly. We have also projection, which collapses onto subset planes or lines, for example, mapping 3D structures into 2D structures. We have also scaling, which adjusts magnitudes, and reflections, which create mirror images. Each of these transformations is defined by how it maps vectors between spaces. These transformations we are speaking of are essential in practice. Computer graphics rely on them for 3D rendering, for example, robotics for motion planning, AI for neural network operations, and image processing for filtering and compression. Ultimately, vector spaces provide the environment, linear transformations provide the action, and matrices provide the computational tools necessary to execute these complex operations. So, at the end, to wrap up, let us review our key takeaways for our lesson. So, vector spaces offer a highly structured mathematical environment defined by strict rules, while linear transformations act as coordinate mappings that preserve these fundamental rules. Matrices serve as the essential numerical layer that allows software to compute these transformations, providing a foundation for robotics, graphics, and machine learning. Thank you for participating and for following along with this video. And we look forward to exploring linear independence, spanning sets, and basis coordinates in next sessions, inshallah.